So in today's lesson we're going to be talking about the mole concept and formulas. This is the unit overall, but we're just going to start talking about this unit in terms of the main objectives for the unit in general and then get into the first lesson. So these are the main objectives for the unit in general. So we're going to learn how to write symbols of elements correctly, identify the molar mass from the periodic table, use dimensional analysis to calculate quantities, calculate molar mass of of elements and compounds, and then convert between a whole bunch of different units. As you can see, there's a lot of vocab that we're going to be dealing with this unit and learning new things. So lesson 1, we're going to talk about symbols, relative atomic mass, and the periodic table. So first of all, like we've mentioned before, each element has a symbol that's given on the periodic table with a unique atomic number for each element. It's really important that whenever you write out these elements, if it has a second letter, you write it lowercase. So for example, if we have CO written out and we had lowercase o, that would mean cobalt, but if we had C capital O, that means carbon monoxide. So those are two very different things, so just be careful with that as we go. In this first lesson here, we're going to talk about a mass spectrometer briefly. These are used to determine the masses of elements and or isotopes. These are very complex instrumentation. Basically, we're just going to talk about the very basics of this instrumentation. There's obviously a lot more that goes on, but just the basics so you understand. Essentially, the first thing that happens is an atom or molecule is passed through a beam of high-speed electrons. This beam of high-speed electrons knocks electrons off of the atom, and then we have a positive ion that's left over. There's an applied electric field that accelerates the ion into a magnetic field, and the interaction changes the path of the positively charged ion. Okay, so there's a diagram down here. Basically, the sample goes in, the positive ions travel through this accelerating electric field after the electrons were knocked off, and then the accelerated ion beam continues through the magnetic field and basically are separated by their mass. So the ones that are the least heaviest get deflected the least, but the ones that get deflected the most are going to be the most massive ions. The bottom line is that you can determine the mass of the elements or isotopes of a certain element. So C12, carbon-12 is the standard. It's assigned a value of 12 AMUs. AMU refers to atomic mass unit. And the masses of all of the other atoms are used relative to this standard. So this is the standard that go to. This also had been determined using a mass spectrometer. Just a side note, in college, you might have the opportunity to use this device. I had done a lab that actually dealt with a mass spectrometer, and also gas chromatography was the first part. But essentially, you were able to use this to determine the amount of phthalates in children's toys. So there's a lot of really cool things you can do with mass spectrometry, since it separates elements based off of their masses after they go through that process we just described. Alright, so if we do an example here, carbon is an example of an element that occurs in nature as a mix of isotopes. A lot of elements do. So there's different isotopes of carbon. So carbon-12, carbon-13, and carbon-14. As you can see, the most prominent one is carbon-12. It has 98%. Carbon-13 is the next prominent with only 1%, and then carbon-14 rarely exists. But you can use this to determine the average atomic mass of carbon. So what you would do is you would take the 98% of that particular mass, which is 12 AMU for carbon-12, and then the next percentage of the next isotope, and add them up. The last one's so minuscule that it's not even counted in here. So again, you take the percentage, you multiply it by the mass for that particular element, or isotope, and then the next one you do the same thing. You can get your average atomic mass based off of all the isotopes. So even though natural carbon does not contain a single atom with mass of 12.01, for when we talk about stoichiometry and when we do these conversions, we want to just assume that carbon is composed of only one type of atom with a mass of that particular mass. This is because those have been calculated based off of all the isotopes, so we're just going to use that number when we go ahead and do conversions. So here's the practice problem that you can try. So you want to calculate the average atomic mass of nitrogen if you know that there are two different isotopes and they have those relative abundances or those percentage. So basically follow the procedure given on this problem right down here and do the same thing and see what you get.